Hello everyone and welcome to Thinking with Mathematical Models 3.1. Our learning target here is be able to examine the relationship between length and width of rectangles using inverse variation. We've been working with linear relationships for quite a while now, and now we're going to take a look at inverse variation. And what that means is we're going to have an equation that's similar to area equals length times width, but let's pretend our area is fixed, that it can't change, but the length and width can change. Well, if that's the case, um, if we set our area at 30 and our length is 1, well, then our width has to be 30 because 1 times 30 is 30. But if our area is 30 and our length is 2, now our width has to go down to 15. See, I have an up arrow here. It means we went up from 1 to 2 for our length, but our width went down from 30 to 15. And if we go up one more, our area is still 30, but now our length is 3. Well, that means our width has to come down to 10, because 3 times 10 is 30. Another way to look at this is we could have this here, and we're going to divide by our length. We're going to take our area, our fixed area, and divide by our length. The area is what's called a constant. We'll get that into that more here later in 3.1 and 3.2. Our aces for 3.1 are 1, 13 through 21, and 38 through 40. Up here I have the y equals mx is a direct relationship because whatever direction m or x goes, m is going to go and stay the same thing all the time. Meaning for each 1 unit change of x, y is going to change by whatever m is, and that's going to wind up being a linear relationship or a straight line. That was a direct relationship. Now we're going to inverse relationship. So how do you find the area of a triangle? We just talked about area equals length times width. So say this is our area, this is our length, this is our width. If we had length of 2 here and width of 4, our area is going to be 8. So we would have an area of 8 in this one. This one we'd have length of 2 and width of x. That means our area, length times width, is going to be 2x. Okay, so hopefully we kind of get that concept ready to go there. And in 3.1 on page 62, it says, in recent years, populations of many small towns have declined as residents move to larger cities. So this town of Roseville, they're going to give lots away to homesteaders. And each lot has to be 21,780 square feet. It says the lengths and widths of the lots will vary, but the area is going to be the same. It says the town planners want a quick way to check lot sizes for the new homesteaders. Well, in 3.1, we're going to take a look at a problem similar to this, not this exact one. To get started off with an inverse variation, we probably don't want to be working with a number that big for you. So we'll simplify it a little bit here, okay? So 3.1a on page 62, remember area equals length times width. And we want to find rectangles with an area of 24 square inches. Well, our length is already determined for us. This is our independent variable. And then width is going to be our dependent variable. So if we wanted to rewrite this, we would have width equals our area divided by length. Okay, so that's our new equation. So if the number I'm going for here is 24 for my total area, if my length is 1, well, 24 divided by 1 is 24. Okay, then 2, if my length is 2, well, area of 24 divided by 2, that's going to be 12. Okay, so you're going to complete this table going through that same process here. Once you've completed the table, I want you to graph it on this graph and see how that changes from our linear relationships. This will not be a straight line graph, okay? So don't try to force that into it, but go ahead and graph that out. And then part 3 of or number 3 of part A says describe the patterns of change in the width of a rectangle as the length increases. So if we look back here on our table, as our length was increasing, what was happening to our width? Number 4, write an equation relating width W to length L for rectangles with an area of 24 square inches. So as I said at the beginning, we were going to talk a little more about a constant, and that our area was a constant, and we represent constant with the letter K. Okay, apparently C was on vacation or something when they came up with this. I don't know. But anyway, constant is represented by the letter K. So if we had length times width equals area, now we have X times Y equals our constant. We need to be able to find Y here. So we need to isolate that. And in order to do that, we need to divide both sides by X. So if we divide by X here and X here, we wind up with Y equals our constant divided by X, similar to how we had width equals area divided by length. Part B, now you're going to do the same thing, but our rectangle is now 32 square inches instead of 24 square inches. So I've already helped you out by writing the equation for you. It's the same as in part A, only we just have a different square area here. And again, I want you to make a table and a graph. Show lengths from 1 to 10 inches, it says here. And then go ahead and do your ACEs, numbers 1, 13 through 21, and 38 through 40. You know, this is a new concept, so if you get some stuck points here, don't be afraid to ask questions, and I look forward to helping you work through those in class.